Hello and welcome. In this video, we're going to discuss parallel current. Current in parallel divides down each branch that we provide. So if we have multiple resistors that are all in parallel, each one of those resistors gets a dedicated current. And we can visualize this with our river analogy here. We know that if we send a certain amount of water flow into a river and it forks off into two directions, we're going to end up with Q2 and Q1 flow. And we see visually Q2 looks to be a little bit smaller than Q3, but all that water that came from the Q1 current flow is in those two branches, right? It can't stay in the middle up here. It can't be left behind. It has to flow down one of the two options for the river. And that is given in this circuit also right here. So here we see that the 6 amps starts out. That's our flow for our current. And we see that the current can divide at the junction node into two directions. One direction has more current flow at 4 amps, and the other direction has less current flow at 2 amps. And we see that 2 amps and 4 amps added together equals 6 amps. So the current entering the junction is also the current leaving the junction. And that's what KCL says. KCL, or Kirchhoff's current law, says that whatever we put into the junction node, our total IT, is going to equal the sum of the branch currents. And they actually identify it somewhat backwards. They say that the algebraic sum of the current entering and leaving the junction is equal to 0, right? We're going to get a net 0. Nothing is going to be left behind in this junction node, just like at this fork in the river here. Nothing is left behind. We don't leave any water at that fork. It doesn't pool up. It doesn't go anywhere else except down the two branches that we provide. And so we can visualize this here on our circuit. You can see that the total current, the biggest current that we have, is flowing in the front half of the circuit here. But as soon as we hit a branch, we see that that big current actually divides in two separate pathways. Some goes down towards R1 and some goes down towards R2. And we do see that the potential, the positive, the red plus signs on the top is our potential. And as it goes across that resistor, we lose our potential down to the bottom, which means that we have a node across the top that is our voltage total. And we have a node across the bottom that is our ground location. That's 0 volts on the bottom. Right? So we lose all of our potential energy at the bottom of our parallel connection. Right? Let us know if you have any questions.